One of the most important themes in mathematics is that once a certain type of mathematical object has been defined, such as a vector space, it's important to be able to create new objects from existing objects. As a simple example, the union and intersection of sets is a way to create new sets from existing sets. So is the taking of Cartesian products and the formation of power sets. In linear algebra, we can use direct sums to produce new vector spaces from existing vector spaces. So we're going to look at that now. Begin with the definition. If V1 through Vn are vector spaces over the same field F, it must be the same field, the external direct sum of these vector spaces, which I will denote this way, and I'll talk about this notation in a minute, is the vector space whose underlying set is the Cartesian product, so it's the set of ordered n-tuples, with component-wise operations. So you simply add corresponding components and you multiply an n-tuple by a scalar by multiplying each component by that scalar. And I leave it to you to verify that's in fact a vector space. As to notation, unfortunately there's not a universally accepted notation for the external direct sum. Some authors will use a plus sign with a circle around it. Some will use the x that's used for Cartesian product. Personally, I don't like the x because it doesn't indicate that there's an algebraic structure involved. I also don't like the plus sign with the circle around it because we're going to use that, as is customary, for something called the internal direct sum. And I'd rather have different notations for the internal and external direct sum. So I use a plus sign with a square around it. It's not standard notation, but as I recall, a couple of the reviewers of my advanced linear algebra book thought the notation was very nice, and so at least that's some validation. Simple example, Euclidean space Rn is in fact nothing more than the external direct sum of R copies of the real, n copies of the real numbers. It turns out that there are two useful generalizations of the direct sum for infinite sequences of vector spaces. So let's look at those two generalizations. Here's the first one. We have a sequence of vector spaces. I should use parentheses rather than braces. And again, they must be over the same field. The strong external direct sum, which I denote this way, it's consistent with the earlier notation, is the Cartesian product of this infinite sequence of vector spaces under component-wise addition and scalar multiplication. So instead of adding two ordered n-tuples, we add two infinite sequences. We still do it coordinate-wise or term-wise if you prefer. And scalar multiplication is similar. Again, this is not difficult to see that this is a vector space. In both cases here, what you're really doing is multitasking. It's though you are performing the operations in each vector space at the same time. So associativity is fairly evident and so on. For the second generalization, we need a definition. Let V be a vector space. An infinite sequence of vectors from V has finite support if at most a finite number of the terms in the sequence are non-zero. So all but a finite number are zero. It's mostly zeros. Now, the set of vectors in the strong external direct sum that have finite support is a subspace of the strong external direct sum, because when you add two infinite sequences with finite support, the sum has finite support. Just for example, if, say, x here had 10 non-zero terms and y had 15 non-zero terms, then x plus y has at most 25 non-zero terms. There may be some cancellation, but you're not going to be able to produce non-zero terms in the sum where both x and y have zeros. So, and similarly for scalar multiplication. So this is the official definition. The weak external direct sum, and I don't really like this notation that much, but it's convenient, and we're not going to use it very much. I put a little subscript W after the notation for the strong external direct sum. This is simply the subspace of the strong external direct sum that consists of the sequences with finite support. Unfortunately, there is quite a variation in terminology in the literature. This is one of the worst abuses, I guess you might say, of terminology. We use this notation: strong direct sum, weak direct sum. Others, however, will use direct product and direct sum, and still others will use Cartesian product and direct product. So you can see it's quite a mess. Our strong direct sum is other people's direct product or Cartesian product. That term, I think, is very misleading. Our weak direct sum is other people's direct sum, and still others direct product. Now look at the direct product as being used in two contradictory ways by others. It's one thing for a concept to have two different names. It's unfortunate, but it happens a lot. But it's another thing for two different concepts to have the same name. That's terribly confusing. So when you read other books or hear other people speak and they use any of these terms, you have the right to ask, what do you mean precisely by that? Just by way of justification, maybe, there is no such thing as a product in vector spaces. There's a scalar product, but there's not an ordinary product. We add vectors, we don't multiply them. So that's why I think that word sum is more appropriate. It indicates the operation, the binary operation in both cases. So that's why I like to stay away from the term product. But I'll make a confession. I grew up using the term direct product the books I used and the professors that were my professors, some of them used the word direct product. So occasionally I will slip and say direct product when I really mean direct sum. So if that happens, I apologize. The external direct sum can be generalized to arbitrary families. And it goes like this. There's no such thing. We lose the term n-tuple, we lose the term infinite sequence if the family is uncountably large. So we have to replace those ideas with something that I call component functions. Otherwise, the ideas are the same. Let's take a little bit closer look at infinite sequences. If you took my transition course, there was a discussion of infinite sequences, and it went briefly something like this. Most people, if you have a set S, a sequence from S, they would simply write this way. They might start the indexing at 1, or even something, some other natural or some other integer, but I'll start at 0. This is not really the formal definition of an infinite sequence. An infinite sequence is a function from the natural numbers, because I'm indexing starting at 0, to the set S, the underlying set. And I called that function little s. So little s of k, here k is a natural number, is often written s sub k. This is the image of the natural number k under the sequence, written s sub k. So this is actually the set of images of the natural numbers, or we would say the image of the function, written in order here, the order designated by the index set, which is the natural numbers. So this is the formal definition. This is the way sequences are commonly denoted. And we can start an infinite sequence at a different index simply by defining it as a function from a different domain here. Say, for example, the domain that consists of the natural numbers bigger than or equal to n, and mapping into the set S. So this would be written little s sub n, little s sub n plus 1, and so on. Okay. So, despite the fact that infinite sequences are technically functions, we generally just write them this way. We need one more definition, and that is to extend the idea of finite support from sequences, which are now, we think of them as functions, to more general functions. If we have a function f from an index set to a vector space, this function has finite support if at most a finite number of these images, f of I, are non-zero. It's exactly the same definition as for infinite sequences. To say there's a finite number of non-zero terms is the same thing as saying there's a finite number of images of the function. Now we can define the Cartesian product of an arbitrary family of vector spaces. In fact, this applies to any sets. And there are, but for vector spaces, there are two types of Cartesian products. Only the first type applies to arbitrary sets, so I didn't include that specifically. The strong Cartesian product of a family of vector spaces, also called the unrestricted Cartesian product, is the set of all functions from the index set of the family to the union of the family. So f of little I must belong to v sub I for all I, little I and big I. And each of these functions I'm calling a component function, because when you think about ordered n-tuples, each entry is a component. When you think about infinite sequences, each entry, usually called a term, but could be called a component. So this is the component. Each of these is a component function. The Cartesian product is the set of all component functions. And again, this would apply to any family of sets, not just vector spaces. But because we are dealing with vector spaces, and because vector spaces have a zero vector, we can define the weak Cartesian product, also known as the restricted Cartesian product, simply to be the set of all component functions that have finite support. This is exactly the same as what we did for infinite sequences when you look at them as functions. Now we can define the direct sums. The strong external direct sum, or unrestricted external direct sum of the family, is the strong Cartesian product under the usual addition and scalar multiplication of functions. And the weak external direct sum, or the restricted external direct sum of the family, is just the subspace of the strong external direct sum consisting of the functions with finite support. We're not going to use the external direct sums for arbitrary families. Maybe I should have said that before I started this short discussion, but it's something very important to understand. It's a concept that's worth thinking about until it makes sense. And so I wanted to bring it up sort of for general education purposes in mathematics. Okay. Of course, for a finite family, strong and weak makes no difference. Every function, every n-tuple has finite support because there are only a finite number of terms. So the two generalizations converge for finite families of vector spaces. Now, the internal version of direct sum is often more useful, and we'll spend a lot more time with it than the external version of a direct sum, even though the two versions are isomorphic, which I know won't mean anything to you necessarily right now, but you can pass between internal and external direct sums at will, and they're equivalent. It's just that the internal direct sum formulation proves to be more useful. To discuss internal direct sums, however, we have to discuss a preliminary idea called levels of disjointness. At least that's what I call it. I have not seen this articulated in other books before. There are 3 levels of disjointness among families of subspaces of a given vector space. The lowest level is simply essential disjointness, which means the intersection of the entire family is trivial. Or put another way, the only vector that lies in every member of the family is the 0 vector. Of course, that must be in every member of the family. The middle level of disjointness is pairwise essential disjointness, which means that if you take 2 distinct indices and look at the 2 subspaces in the family with those indices, their intersection is trivial. I should note that this is not the same as saying 2 distinct members of the family are essentially disjoint, because 2 different indices could produce the same subspace. Families could be multisets. So I have to be very specific about saying if the indices are different, the 2 indexed subspaces are disjoint. So in this case, there cannot be any duplicates unless it's the trivial subspace that can appear more than once in the family. Okay, so this is pairwise essential disjointness. There is an analog that you should be familiar with. Let's say 3 natural numbers can be relatively prime, or they can be pairwise relatively prime. And they're different concepts. Pairwise relative primeness is stronger. So for example, 2, 3, and 4 are relatively prime because they have no common factor other than, well, plus and minus 1, positive and negative 1. But they're not pairwise relatively prime because 2 and 4 are not relatively prime. So this is the analog for subspaces and essential disjointness. But, and here's an example if you would like to look at it. In R3, the plane is S1 here, and this x-axis I denoted by S2. These are, and S3 is the z-axis. These are essentially disjoint because when you intersect all 3, you get the origin. But they're not pairwise essentially disjoint because S2 and S1, their intersection is not trivial. It's just S2. Because we have an algebraic structure, what we've talked about so far, disjointness and pairwise disjointness, would apply to arbitrary sets. You would drop the word essential. But because we are dealing with an algebraic structure, there's a 3rd level of disjointness that's even stronger than pairwise essential disjointness. Take a look at these 2 pictures. Again, we're dealing with R3, and on the left here we've got 3 lines that lie in the xy plane. On the right here we've got 2 lines, L1 and L2, in the xy plane, and L3 is not in that plane. Now in both cases, the 3 lines those are subspaces because they go through the origin, are pairwise essentially disjoint. Take any two of those lines and intersect them, all you get is the origin. But these three lines have a higher level of disjointness than these three, because no vector in any one of these lines is equal to a sum of vectors from the other two lines. Here, that's not the case. In fact, when you take the sum of any two of these lines, you get the whole plane, which contains the third line. Okay. So the lines or subspaces on the right here have this property. L1 intersected with the sum of L2 and L3 is trivial, and these are similar. That is a higher level of disjointness than simply pairwise essential disjointness. So in summary, we have these three levels of disjointness for a family of subsets. The intersection is trivial, that's essentially disjoint. Pairwise essentially disjoint. Two different indices, the subspaces are essentially disjoint, and strong essential disjointness. Each subspace is essentially disjoint from the sum of all the other subspaces. And each of these properties is stronger than the previous one. Here's an example. The subspace L0 of lower triangular n by n matrices with zeros on the main diagonal. So I called them strictly lower triangular matrices before. The subspace of strictly upper triangular matrices and the subspace of diagonal matrices, these are strongly essentially disjoint. Strong essential disjointness will turn out to be quite important for us, and so it deserves a little bit more scrutiny. Like most important mathematical concepts, there are several useful ways to characterize strong essential disjointness. This is a theorem with three parts. Part one is the definition of strong essential disjointness. Part two provides a convenient way to test for strong essential disjointness, and part three is the reason that strong essential disjointness is so important. So let's take a look at this theorem. We have a family, non-empty family, of distinct subspaces of V. And the following are equivalent. The family is strongly essentially disjoint, and again, that's the definition. The zero vector cannot be written as a sum of non-zero vectors from distinct subspaces of F. And that is, well, maybe the easiest way to test for strong essential disjointness. We write an equation with equals 0, and we see if it can hold or not. Uniqueness of expression is the reason that strong essential disjointness is so important. Every non-zero vector v in the sum has a unique expression up to the order of the terms as a sum of non-zero vectors from distinct subspaces. All right, let's look at the proof. As far as 1 implies 2, strong essential disjointness implies that the 0 vector is not a non-trivial sum. Suppose 2 fails. Suppose that 0 can be written as a sum of non-zero vectors from distinct subspaces in the family. If S1 belongs to, let's say, the subspace capital S sub k, we could move S1 to one side of the other side of the equal sign and have an equation like this. But now negative S1 belongs to Sk, and this sum belongs to the sum of the other subspaces, all the subspaces except for S sub k. And that violates strong essential disjointness. So if 2 fails, 1 fails, therefore 1 implies 2. Next, we assume 2, and that is to say the 0 vector is not a non-trivial sum from the family, and we need to show that there is uniqueness of expression as a sum for non-zero vectors. Okay, so for that, we can assume that 2 holds. And that a vector v, a non-zero vector, can be written as a sum S1 through Sn, and also as a sum T1 through Tm, where the S's are non-zero and belong to different subspaces of the family, and similarly for the T's. And our goal is to show that N and M are equal and that the S's are the same as the T's. So that gives us unique expression up to order of terms. Okay. Well, first of all, we can put everything on the same side as we can subtract. So we take the sum of the S's and we subtract the sum of the T's, we're going to get 0. So that looks like this. Now we don't know initially if the S's, any of the S's are equal to any of the T's. It's a little bit of a mess. So what we can do is reindex, say, the T's if necessary, so that if S1 is T5, then we'll reindex T5 to T1. So what we can do is we can assume, after all this manipulation of indices, that these pairs have the property that the 2 elements are equal. I'm sorry, not equal, belong to the same subspace. S1 and T1 belong to the same subspace. Sk through Tk belong to the same subspace. But no other pairs have that property. So we regroup. S1 minus T1, these are both in the same subspace of the family up to Sk minus Tk. So now Sk plus 1 is in a different member of the family than any of these other terms. And similarly for the T's. But now we have a representation of the zero vector. And since we're assuming that there is no non-trivial representation of the zero vector, all of these terms have to be zero. But the s's are not zero by assumption, and the t's are non-zero also by assumption, and so there can't be any of these last groups. So in fact, not only are these terms missing, they don't exist, but these terms are zero. So what we are conclude is that n is equal to k, m is equal to k. In other words, n and m are equal, and S1 equals T1 all the way up to Sn equals Tn. So the s's are the same as the t's, except for, again, the order of the terms. And that proves that 2 implies 3. I'm going to add some square brackets here. It might make this a little easier to read. Finally, we have to show that 3 implies 1. So the essential uniqueness, I'll go back here, the uniqueness of expression for non-zero vectors implies a strong essential disjointness. If the family is not strongly essentially disjoint, that means there's a non-zero vector, we should write non-zero here, that is in one of the subspaces of the family and also in the sum of the other subspaces. But that means that V has two different expressions as sums of vectors from distinct family members. One is the trivial expression, because V is equal to V. It's just a one-term sum, and that belongs to SI. But because of this, V must also be a sum of vectors from the other family members. So that violates 3. So if 1 fails, 3 fails, therefore 3 implies 1. And that completes the proof. Now we can define the internal direct sum of a family of subspaces of a vector space V. And it is simply a strongly essentially disjoint sum. We've already defined the sum of subspaces, and we showed that it's the same as the join. If the family is strongly essentially disjoint, then we refer to the sum as an internal direct sum of the family, or just simply a direct sum of the family of subspaces. Each subspace in the family is called a direct summand of V, and this is the notation we'll use. Now we're going to use the plus sign with the circle. And for a finite family, it looks like this. We will very often encounter a direct sum of just two subspaces, And in this case, each subspace is referred to as a direct complement of the other, or simply a complement of the other. Example, if we have three distinct non-coplanar lines in R3, they're strongly essentially disjoint, and their sum is all of R3, and therefore the sum is direct, and we can write this. It's important to note that if S and T are subspaces of a vector space, we can always write the sum. The sum always exists. It's just the set of sums of a vector from S and a vector from T. But to say that the direct sum exists, or even just to write this, is to imply that the two subspaces are, well, strongly essentially disjoint, but in the case of two subspaces, it's the same as just being essentially disjoint. So the direct sum doesn't always exist. The sum always exists. The direct sum of two subspaces exists, even if it's not all of V, if and only if S and T are essentially disjoint. And more generally, the direct sum exists, direct sum of any family exists, if and only if F is strongly essentially disjoint. So when you write this, or you use the term direct sum, you are implicitly implying that the family is strongly essentially disjoint. Let's take a look at these two pictures. P here is a plane through the origin in R3. Each of these lines is a complement or direct complement to P. In fact, any line that is not in the plane, do it again. Look at these pictures. P is a plane in R3. Any line that does not lie in the plane is a direct complement to P, or put another way, the line and the plane are direct complements of each other because their sum is all of R3, and because they are essentially disjoint, or strongly essentially disjoint, but again, for two subspaces, that just means essentially disjoint. Here are two planes, distinct planes in R3. These are not direct complements of each other because they're not essentially disjoint. Here's another example of direct sums. Any matrix of size n by n can be written this way. A can be written as 1/2 A plus A transpose plus 1/2 A minus A transpose. And it's not hard to see that this first term is a symmetric matrix and the second term is skew symmetric. So we can say that every matrix A is the sum of a symmetric matrix and a skew symmetric matrix. But the symmetric matrices, let's say SYM, and the skew symmetric matrices are essentially disjoint, because if a matrix is both symmetric and skew symmetric, it has to be the zero matrix, and I'll let you fill in the details. So this sum is actually a direct sum, an internal direct sum, but we again usually just say direct sum. It is a fact that every subspace of a vector space has a direct complement. Now, the usual proof of this fact is given after a discussion of bases, and that will simplify the proof. It actually doesn't really simplify it, it just appears to simplify it. But we haven't discussed bases yet, and so we're going to prove this fact directly, and that requires the use of Zorns Lemma, which is discussed in Appendix B of the book, and we discussed it in an earlier lecture. It's good practice using Zorns Lemma. I guess it's our first experience with it in this lecture series, and so that's what we're going to do. Actually, the proof, the more common proof using bases, doesn't really avoid the use of Zorns Lemma, because the establishment of bases, the fact that every non-zero vector space has a basis, requires Zorns Lemma. So we're just sort of transferring Zorns Lemma, or its use, from this that we're about to do to the existence of bases. So one way or the other, all of this depends on Zorns Lemma, so we might as well see how it applies directly. Any subspace S of a vector space V has a complement. Specifically, there exists a subspace T for which V is the direct sum of S and T. Now, for this proof, we will consider the family of all subspaces of V that are essentially disjoint from S, because T is essentially disjoint from S, if it exists, so that it will be found in this family. So that's the family of subspaces that we need to study. First of all, that family is non-empty because the trivial subspace is essentially disjoint from S. And of course, that family is partially ordered by set inclusion, because they're just subspaces. We want to show that this family has a maximal element. Because if S does in fact have a complement, that would certainly be a good candidate. A maximal subspace of V that is essentially disjoint from S. So, to find a maximal member of a partially ordered set, we use Zorns Lemma. Suppose we have a chain of subspaces in this family. So each of these is a subspace of V that is essentially disjoint from S. An earlier theorem, 1.32, tells us that the union of this chain is a subspace of V. We proved that right after we proved the fact that, in general, the union of subspaces is not a subspace, but for a chain, it always is. Moreover, because every member of this chain is essentially disjoint from S, the union is also essentially disjoint from S. And so it belongs to the family. But, finally, U is an upper bound for the chain. The union is an upper bound. It contains every member of the family. Those are the conditions for Zorns Lemma. Every chain has an upper bound. And so Zorns Lemma does tell us that the family has a maximal subspace. We'll call it M. So it's a maximal subspace of V that is essentially disjoint from S. And the plan is to show that M is in fact a complement of S. Because S and M are essentially disjoint, we know the direct sum exists. So all we have to do is show that the direct sum is all of V. But if it's not, then there's a vector little v in the vector space that's not in the direct sum. We need a contradiction. Essentially, the only thing we can contradict is the maximality of M. So let's form this subspace. It's the sum of M and the subspace generated by this vector V that does not lie in S plus M. So that looks like the set of all sums of vectors from M and vectors from this subspace. So it's a U plus AV where U is in M and A is a scalar. But this subspace is essentially disjoint from S as well, because if a little s in here, so that would be a U plus AV, belonged to capital S and was non-zero, then A has to be non-zero because S and M are essentially disjoint. So U cannot be, since U is in M, it can't be in S, so A can't be 0. So we can write V here is equal to A inverse times the quantity S minus U. We'll move the U to the other side. That is in this direct sum, but that contradicts the fact that we took V from this set. V is not in the direct sum. So that's our contradiction. And so this subspace also belongs to the family F. It's essentially disjoint from capital S. And now we're in trouble because M was supposed to be maximal with respect to being essentially disjoint from S. But this is strictly bigger and is essentially disjoint from S. So the only way out is that there is no little v in this set difference, and so S plus M is in fact all of V, and M is a complement of S. This is a typical use of Zorns Lemma, and I would strongly suggest you go over this proof until it all makes sense.